Hello everyone, welcome back to Math with Allison. Today we're doing another exam. So this is for Calculus 1. This is the second exam typically. It's all about the first portion of the derivative content. So this is from 2015. The professor gave me permission to do a YouTube video on it, and they also gave me permission to give it to you guys. So the PDF is linked down below. If you want to work on it beforehand and then check your answers with this video, that's great. If you want to work on it while we go through it, that's also great. Whatever you want to do with it, it is up to you. So let's go ahead and go through this video. I love that first off, they tell you how many problems there are and how many points they're each worth. That's really great to look at the beginning. Otherwise, we're just going to go ahead and go into it. So first, we're going to go ahead and talk about the limit definition of a derivative. So in part A here, they want you to write out the limit definition officially. So here we have this. They want us to go ahead and write this out so we can actually apply the limit definition in part B. So we have what f of x is equal to, and we want to go ahead and prove using the limit definition that its derivative is 4x minus 3. So first what I suggest we do is we write out f of x plus h. What we want to do here is everywhere we see an x, which we have right here and here, we want to replace that with x plus h. So I'm going to go ahead and do that. Let's go ahead and try to simplify this out a little bit before we plug it into the limit definition. So here, let's go ahead and square that x plus h. So I get x squared plus 2hx plus h squared. And then we can go ahead and distribute this minus 3. So we get minus 3x minus 3h. Again, we can go ahead and distribute this 2 everywhere. So I'll go ahead and do that. Now that we got this all simplified out, we can go ahead and plug it into our limit definition. So notice right here, I had to put the actual function in parentheses because we have to remember to distribute out this minus. I can't tell you how many exams I've graded and people forget to distribute that minus sign. So let me go ahead and do that. So now our next step here is to see if anything cancels out. And so I notice here that this 2x squared minus 2x squared cancels, and the minus 3x plus 3x cancel. So I'll go ahead and rewrite it with our leftovers. So remember, our goal here is to get rid of that h in the bottom, and we can go ahead and do that by dividing out an h from every single term. Now that we've got rid of that h in the denominator, we can go ahead and plug in what h is approaching. So we have h is approaching 0, and I only have one h value left. So here I get 4x minus 2 times 0 minus 3, but we can go ahead and simplify that to 4x minus 3. So if we look at what the problem was asking us to do, we prove that the derivative is equal to 4x minus 3. So we are good with that problem. Let's go ahead and move on to the second one. So here we have true and false questions. We do not need to give justification. We just need to answer true and false. So first for part A, we have f of x is differentiable at x equals a, then f of x is continuous at x equals a. This is a true statement. If it was not differentiable, then it would not be continuous. Now for part B, we have the tangent line to y equals x to the 1/3 at the point 0, 0 has a slope of 0. So remember, in order to find the slope of the tangent line, we need to find the derivative. So let's go ahead and find y prime. Here I'm going to use power rule, so I get 1/3 x to the negative 2/3. And I'm going to go ahead and rewrite that because I can bring that x to the negative 2/3 to the denominator, and that makes it positive. Now what we want to do is plug in our value of 0, 0. So we get y prime is equal to 1 over 3 times 0 to the 2/3. Now, if we look at this, we get 1 divided by 0, which is super illegal. So this one is going to be false because actually the slope is just going to be undefined. So we have a false statement right there. For part C, if f of x is greater than or equal to 0 for all x values and f prime of x exists for all x, then we have that the derivative is greater than or equal to 0 for x as well. Let's go ahead and think about this. If the derivative is greater than or equal to 0, then that means our function is always going to be increasing. So we have a constant increasing function. But if I go ahead and draw an example where our function is always greater than 0, something like this, well, it's always greater than 0, but I have some cases where it's not increasing. Look right here, it's decreasing, decreasing, decreasing. And so this is going to be another false statement. Just because it's greater than or equal to 0 does not mean that it will be increasing the entire time. Now for part D, for any differentiable function, we have that the derivative of a quotient is equal to f prime x over g prime x. Now this is going to be a false statement, and I know that just because of the quotient rule. For part E, this is claiming that the third derivative in d cubed over dx cubed represent the third derivative of f of x with respect to x. This is a true statement. We're just going over two different notations. Now for part F, if an object's position function s of t equals 2t cubed minus 3t squared, then the object's velocity and acceleration are both 0 at t equals 0. We can actually go ahead and solve for this. So in order to find the velocity, I'm going to take the first derivative of our position function. So this means I get what? 6t squared minus 6t. Let's go ahead and plug in the time t equals 0. So we get v of 0 is equal to 6 times 0 squared minus 6 times 0, which is indeed equal to 0. So we got the velocity. Now let's go ahead and find the acceleration, which represents the first derivative of velocity and also the second derivative of the position. So I'm just going to go ahead and take the derivative of this, and I get 12t minus 6. Now, if I were to plug in t equals 0, I get 12 times 0 minus 6, but this is equal to negative 6, which is not going to be valued 0. So here we got another false statement. Just because a problem says you don't need to show work, it doesn't mean you shouldn't show work. Sometimes you got to work through the problem a little bit. So now here we're going on to part 3. We're going to go ahead and use the standard rules of differentiation. So let me go ahead and write this for part A. We're going to rewrite it. I got x to the power of 6 plus 4x squared minus, and I'm going to rewrite that to the power of 1/2. That way when I take the derivative, all I need to use is power rule. So if I do that, here I bring down that value 6 and I subtract 1 from the exponent. And I do the same thing. I have 4 times 2, which is equal to 8x to the power of 1 minus 1/2 x to the negative 1/2. Notice that in this problem, it doesn't say we have to simplify it, which means we're going to take the lazy way out, guys. Try to save time on your exams. If it doesn't say simplify it, don't simplify it. Now we're going to go ahead and compute the second derivative of this function. So let's go ahead and compute the first derivative. We have the derivative of e to the x is just e to the x, plus the derivative of the natural log of x is 1 over x, minus, and the derivative of sine is equal to cosine of x. So here we have the first derivative, but we can't stop here. Let's go ahead and find the second derivative. So here we get e to the x plus, but now how are we going to take the derivative of 1 over x? Well, I'll write that over here. 1 over x can be rewritten as x to the negative 1, which means we can apply power rule. That negative 1 comes down, and then we subtract 1 from the exponent, so that becomes negative 2. Now the derivative of cosine is equal to negative sine. Again, you could just leave it like this, but I'm going to simplify it because that bothers me a little bit. So this becomes e to the x minus 1 over x squared plus sine of x. Again, you don't need to do that. I just did it for myself. Okay, we want to go ahead and find the derivative of g. It looks like here we're going to go ahead and have to use product rule. The reason I know that it's product rule is because we're working with multiple variables. So everything in here has a t and everything in here has a t. So when we have multiple t's like that or multiple variables, we need to apply product rule. Alrighty, let's go ahead and find our derivative. So first we get the derivative of f is equal to what? 30t plus 14. And then the derivative of g, if we remember, is going to be secant squared of t. So let's go ahead and use product rule. We start at the bottom, work our way to the top. We multiply those together. So let me write this out. Now we're going to go ahead and add the opposite multiplication. Now for part D, it looks like we're going to have to go ahead and apply quotient rule. So here we have the numerator and the denominator, and I'm going to go ahead and set it up. Alrighty, so we get the derivative of f is going to be 6t plus 5, and the derivative of g is going to be 2t. So now with quotient rule, we do have to be careful about our ordering, which is why I always keep it the same with product rule. So here we start at the bottom, work our way to the top. And now we have to subtract from the top, work our way to the bottom. So here we get, and don't forget we have to divide by the denominator squared. So we get t squared minus 2 quantity squared. Again, don't simplify. Leave it like that. Now we can move on to problem 4. So again, we're going to have to use derivatives. So here we have the derivative of the natural log of e to the 2x plus secant of x. Here, this is where I know I'm not going to use product rule because we only have one portion that's with our variable, and that's going to be the inside. The natural log part doesn't have an x attached to it, so it's not two products. It's the natural log of that whole thing. So let's go ahead and apply the natural log rule. So the natural log rule is where you take the derivative of the inside. So we get 2e to the 2x plus, and that becomes secant of x times tangent of x. And then we divide by everything on the inside. So that just remains the same, e to the 2x plus secant of x. I'll go ahead and write that out. So what I mean by square is the inside. So 1 over the inside times the derivative of the inside. Or we can rewrite that as the derivative of the inside all over the inside. You could also set it up with chain rule, but whatever your heart desires. Now for tangent, we need to remember the derivative of the inverse tangent. And so when we do that, we have to do 1 over the inside squared plus 1 times the derivative of the inside. Or we can rewrite that again as the derivative of the inside divided by the inside squared plus 1. So if I do that, I take the derivative of the inside, which is going to be 2t, and I divide it by the inside t squared plus 1 quantity squared plus 1. And that is our answer. Again, take the lazy way out. Don't simplify it. We can do the same thing with the inverse sign. So if we remember that derivative, we have 1 over the square root of 1 minus the inside squared times the derivative of the inside. Or once again, we can rewrite that as the derivative is on the numerator and we have that in the denominator. So if I do that, I want to take the derivative of the inside. We get 0 minus, and now what we actually have to use here is chain rule. So think about this as the inside is tangent and the outside is the power of 2. I'll go ahead and set up chain rule so we can see that. So here we get the derivative of tangent is going to be secant squared of x. And then we have the g prime of u is equal to 2u. So if I set that up, I get secant squared of x times 2 of the inside. I'll replace that back in. And so this is our numerator. And in the denominator, we still have to do the square root of 1 minus the inside. So that is 2 minus tangent squared of x, quantity squared. And this right here is our final solution. So remember, with all of these, you can set it up individually with chain rule. It's just going to be whatever you like to see. Moving on to problem 5, we're going to go ahead and use logarithmic differentiation in order to find the derivative. I don't like working with the f, so I'm going to go ahead and rewrite that as y. And in order to do logarithmic differentiation, you take the natural log of both sides. So the purpose of doing this is because the exponent comes out front. So now what we need to do is take the derivative of both sides, and we're going to take the derivative of both sides in terms of x. So when we do that on this left side, we get 1 over y times the derivative of y. And now on this left side, it looks like we're going to go ahead and set a product rule. I have lots of x terms in here, and I have lots of x terms in here, which tells me I need to use product rule. Okay, let's go ahead and calculate these derivatives. So first, f prime is equal to 3x squared. And now g prime is going to be, so the derivative of the inside is going to go in the numerator, and that becomes 2x. And in the denominator, just whatever was on the inside, so x squared plus 1. So now that we have these multiplied out, we can go ahead and do the cross multiplication and add them together. So remember, what we're trying to solve for was f prime of x, or the y prime, because I changed that to y. So in order to do that, I'm going to have to multiply both sides by y in order to get that all by itself. However, I don't want my final answer to have any y's in it, so I actually have to go back and replace what it was equal to. So instead of y being here, I'm going to have what it was originally equal to. And boom, we have it. That's our final answer. So now for problem 6, we have the curve x cubed plus x times y plus 2y cubed equals 4. And we want to go ahead and use implicit differentiation in order to find the slope of the tangent line at the point 1, 1. So implicit differentiation, I'm going to go ahead and take the derivative of both sides of this equation right here in terms of x. Alrighty, so first let's take the derivative of x cubed. That's going to be totally fine because they're the same variable. So we get 3x squared plus. Now we're going to go ahead and have an issue because we have two variables that are being multiplied by each other, which means we're going to have to set up product rule. So the derivative of x in terms of x is just 1, but the derivative of y in terms of x is just going to be the first derivative of y. Now we get to cross multiply these and add them together. Alrighty, so finally we're going to go ahead and take the derivative of 2y cubed. First, we're going to take it like it's a normal derivative, so we drop down that exponent and we get 6y squared. But now we have to multiply by the derivative of y, so I'll leave that as y prime. And now we have the derivative of a constant is always equal to 0. So now let's go ahead and look at our y primes. I have a y prime right here and a y prime right here. I'm going to keep all my y primes on one side, and I'm going to move over my non-y primes to the other side. So the purpose of doing that is so I can pull out a y prime on this side, and now I have my leftovers x plus 6y squared. And now I can get y prime all by itself by dividing over that whole term. And now what we want to go ahead and do is plug in our point. So our point is 1, 1. So here this tells us that x equals 1 and y equals 1. And I can go ahead and plug that into my equation. And here we have the slope of our tangent line. So right here is our value, and we can actually go ahead and check this with the graph. So the point 1, 1 is going to be right here, and as we can see, the tangent line is going to be something like this, which has a slope of -4/7. We have an insect crawls on the ellipse 2x squared plus y squared equals 11. At the instant the insect passes through the point 1, 3, its x-coordinate is increasing at 1 unit per second. So this is going to tell us that the derivative of x in terms of time, because we always work in terms of time in real life problems, is going to be 1. Or you can write this as x prime equals 1. We want to go ahead and find the rate the y coordinate is changing at that same instant. And so we want to go ahead and find y prime or dy dx. So let's go ahead and pick out one more piece of information we know, and that has to do with our point. The point 1, 3 tells us that x is equal to 1 and y is equal to 3. So let's go ahead and set up our implicit differentiation. We want to take the derivative in terms of time of both sides. So let's go ahead and do that. First, we're going to take the derivative of 2x squared. So I'm going to treat it like normal power rule, and I get 4x, but now we have to multiply by x prime. Same thing with the y. I'm going to bring that down that power, and I get 2y times y prime, and the derivative of a constant is equal to 0. So now let's go ahead and plug in the information we know. I get x is equal to 1, I get x prime is equal to 1, I get y is equal to 3, and y prime is what we're trying to find. So if I multiply that, I get 4 plus 6y prime is equal to 0. Subtracting 4 from both sides, I get -4 over there. And now I can divide everything by 6, and I get y prime is equal to -4/6, or you can simplify that down to -2/3. So this can be our final answer. It depends on your professor if they want you to write it out all fancy. I'll go ahead and do that for those who like to see it. So that's how I would write it out all fancy. But this is the exam. We got 100%. Good job, everyone. So this is all I have for us today. If you enjoyed this video, I have many more like it, so make sure to check out my playlists. They're linked down below. Otherwise, please give this video a thumbs up and comment other topics or problems you'd like to see done. Thanks for watching.